Hello, and welcome to Lesson 1.2, Algebraic Expressions. Our objective for today is that I can write algebraic expressions for verbal expressions, and I can evaluate algebraic expressions. Now, you might be asking yourself, what is an algebraic expression? It is an expression that contains at least one variable. What is a variable? It is a letter used to represent an unspecified number or value. Now we have a couple other vocabulary words here. So a term is an expression that is a number, a variable, or a product or quotient of numbers and variables. A variable term is a term that contains a variable, and a constant term is a term that does not contain a variable. So let's look at some examples here. A term, it could be something like 3x, 4y, x squared, 3 times, let's say x, y, right? Those are all different expressions or different terms that could exist. So those are also all variable terms. They have a variable in them. A constant term is going to be something just like this, and it'll usually be at the end of an equation where it'll be like a +7 or a -6, right? A number by itself. That's it. Just a number. That is a constant term. It's constant because there's no difference to it. It's not being multiplied by anything, so no matter what, it will always be that value, thus constant. So let's write some verbal expressions. We're going to start with A and D here. First off, we have 4 and x. We've got 4 times x. So if we look back and think back to the some of the vocabulary words that we worked on yesterday and ways to say these different operations, 4 and x next to each other, remember, we have that imaginary multiplication dot in between two things that are next to each other like that. So we could say something like 4 times x. That is a simple way of saying that. Letter D, we could write that as, we've got division, so we could say the quotient of 7 and a number y. We'll specify that the variable is y. Do you have to say and a number y, or could you just say and y? And y would be perfectly acceptable as well. Okay. Letter B. We've got a whole bunch of different ways to say we are adding. I'm going to choose to say the sum of 15 and r. You could say 15 plus r, the total of 15 and r. Those are all options that you could use. This is the one that I chose for this. Okay. Now, letter E, we've got an exponent involved here. And so there's a fancy word for an exponent of the third power, and it is cubed. So I'm going to say x cubed. And we are multiplying that, or times 4. And I'll write it as a word this time, instead of just a number. So x cubed times 4. X to the third power times 4. That's exactly what we showed. Could you have said 4 times x cubed? Absolutely, you could have. So letter C, let's write it in that pattern. So we're going to say 3, and we are multiplying that. So 3 multiplied by, and we have x, and we are to the second power, and the mathematical way of saying to the second power would be squared. So the total phrase would be 3 multiplied by x squared. All right, letter F here, we've got subtraction, and so we could say all kinds of stuff. I'm going to say it in a way that is going to the heart of some phrasing that you'll see in word problems that might be a little tricky at times. And I'm going to say this is going to be, and I'll do it in words, 5 less than x, right? 5 less than x. We are taking 5 away from x. It's going to be whatever x is, we want to know what 5 less than is. We're going to go down 5 from there. All right, so that brings us to our you try problems, and I want you guys to try those on your own, pause the lesson, and then come back and check your work against mine. All right, so the first one, we have 3 to the 5th power, and so we are going to, there's no fancy way of saying to the 5th power, so we're just going to say 3 to the 5th power. So there's squared and cubed. Anything beyond the third exponent is you just say to the whatever power, to the third, to the 9th, to the 27th power. Whatever that may be, that's just what you say beyond squared and cubed. All right, letter H. We have subtraction again. So let's say we could say this one as the difference And when we say difference, we always put the first term that's listed first, the difference of y and 23. '23 being a very good number. And letter I. We have 8 over x. We've got division going on here, so we could just say the quotient of 8 and x. Okay, so we have the quotient of 8 and x. All right. We are going to move on to our second example in this section of the text, and it is example 2, write a verbal expression with grouping symbols. So these are going to be a little bit wordier as we look at them. So the first one, we have x squared plus 6x over 7. So how can we say that not the way I just said that? How can we say it, explaining the mathematics that we are doing? So we could say something like the square of x So the square of x plus the quotient of 6 times x and 7. Now, when we look at the quotient and the way we write it out, when you've got the word and with a quotient, that's going to tell you the break between your numerator and your denominator. And is that kind of like separating word of what's on top and what's on bottom. So you know that the 6 times x, that's going to be in our numerator, and then the 7 is going to be in our denominator. All right, now we're going to look at letter B. We have parentheses 3x minus 5 plus 3. So how do we say this? So we can, the plus 3, we can say 3 more than, because we're adding 3. So 3 more than, and now we need to deal with the parentheses part. So we can say the difference of the product of 3 and x. Again, the and, that's telling you what the product is involved with. Those are the two pieces that are going together in that product. So we have the difference of the product of 3 and x, and then we go back to and again. So now this is the and that is separating out the difference, the subtraction, so we have and 5. All right, letter C. We have x plus 5 over 3, so how can we say that? We can say the quotient, because we're dividing, of the sum. So we're saying, what is the sum of? The sum of x and 5. So we have the quotient of the sum of x and 5 and 3. That's going to finish out our quotient portion. We're going to divide it by 3, so we have the and 3 there. So we have 3 you-try problems for you to try on your own. Pause the video here, do the work, come back and check your answer with what I have. All right, letter D, we have x plus 5 and x minus 4, and we have a fraction there. So we could say the sum of x and 5 divided by, and now let's look at the bottom part, we have the difference because we're subtracting of x and 4. All right, so we have the sum of x and 5 divided by the difference of x and 4. So by saying the sum of and the difference of, we are indicating that there's parentheses there and there's something a little more complex going on. So letter E, we've got 8x plus 3 and then minus 9. We have parentheses in there. So we can say 9 less than, all right, that's this portion of it. And now we need to deal with the parentheses, and we've got a plus sign, so we have 9 less than the sum. So our parentheses is the sum of, and we have this piece right here. So we say 8 times x, and then we're going to finish out with the sum with and 3. So 9 less than, we're taking 9 away, minus 9. The sum of, so we have the fraction, we have the parentheses, 8 times x, so that's the first term, and 3, which is the second term in our parentheses. All right, if we look at letter F now, we have x minus 8 over 5, so we could say we have the quotient of, and now let's look at the top. We've got parentheses, the difference, so we have the quotient of the difference of x and 8, and we go back to finishing the quotient and 5, right? Because we have 5 being the second term in the division. The first term was x minus 8, the second term was 5, and that's where the and comes in. Okay, so we're going to take a look at our next section, which is example 3, write an algebraic expression. Okay, so we're going to write an algebraic expression here. We have 2 times the quantity y plus 11. So 2, let's zoom in a little bit. So we have 2 times the quantity y plus 7. So that tells us times the quantity is parentheses y plus 7. Not 7, 11. Okay. So now let's look at letter B here. We have a number n, so I'm specifying what your variable is going to be. cubed, which means to the third power, is increased by, we're adding 5. So we have n to the third power plus 5. All right, zoom out a little bit. 18 increased by the product of 3 and a number x. So 18 increased by, that tells us we're doing addition. So we have 18 plus the product of 3 and a number x. The product of 3 and a number x. Now, can I write this as 3x plus 18? The answer is yes, and we are going to talk about what property that is in our next lesson. All right, now we've got 3 you-try problems. Please go ahead and do those 3. Pause the video, come back, and check your work when you are done. Letter D, we have 5 more than the product of 3 and x. 5 more than tells us we are adding 5. So we have the product of 3 and x, and we are adding 5. You could also have written it as 5 plus 3x, and that's my like squiggle, alternate universe kind of thing. Now, letter E, we have the product of 7 and the quantity x minus 11. So we have 7 on the outside. The quantity tells us parentheses x minus 11. And our last of these you-try problems, 4 less than n to the 4th power. So we have 4 less than, that means minus 4. We have n to the 4th power. So we have n to the 4th power minus 4. Okay. So now let's move on. We've got some examples here. Some word problems, because like I said, word problems, these are going to keep coming back. So we have the cost of bowling is $5 per person for shoe rentals and $45 per hour to book a lane. Suppose a group of friends go bowling one night. So, and we're going to assume that we are working with, actually, no, we could, I say we define a variable here. So we've got, in words, let's say this. We've got 5 times people, and we are adding 45. So define a variable. You could use whatever letter you want in order to define a variable in an algebraic expression. You just need to show what you are defining it as. So in this case, I'm going to go simple, and I'm going to say x equals people. So the way we could rewrite this is 5x plus 45. And this would be assuming that we are just going for 1 hour. We could do multivariables, which we'll take a look at in the next one regarding Lollapalooza. Now, Lollapalooza, and these are the actual costs for a 1 day and 4 day passes for the 2024 Lollapalooza this past summer in Grant Park. So Lollapalooza offers 1 day and 4 day passes. A 1 day pass costs $149, and a 4 day pass costs $385. Write an expression for the total ticket sales. So how much are they going to make total on Lollapalooza? So write an expression for the total ticket sales. Well, if we put this in words, we have 149 times the 1 day passes. Okay, 149 times 1 day passes, plus we have 385 times 4 day passes. Well, okay, that sure seems like I've got like 2 things going on there. Well, we're saying here we're going to define 2 variables. So our first variable, I'm going to use x equals 1 day, and y equals 4 day. So if we write this as an algebraic expression, we have 149 times X, $149 per day times the number of one-day passes, plus 385 times the number of four-day passes sold, which is Y. This is the importance of defining your variables. If you're not defining them, I don't know exactly what you're talking about in any particular part of your problem. So now I want you guys to try this next one, and we will talk about it. All right, so the next one. The cost for tickets to see a new movie is $11.50 for adults and $8.50 for children. Write an expression for the total ticket sales. So total means we are adding adults and children. So let's start with, we've got 11.5 times adults plus 8.5 times children. We'll clean that up a little bit. All right, so we have times children. All right, so now let's define our variables. I'm going to keep it, well, no, we could do a little bit different. We can say, A equals adult, and we could say that C equals child, right? Though we can use any variable we want, any letter we want. We could use Greek letters if we wanted, and later on in the year we will. So we could use whatever value we want or whatever variable we want. So adult and child, A and C, those are logical variables. I don't really need to see much definition if I see A and C in this equation, because I know that we're talking about adults and children. So let's write this expression. We've got 11.5 times the adults tickets plus $8.50, 8.5 times the children tickets. And there we go. We've got an expression that we could use. All right. Example 5, evaluate an algebraic expression. So we are going to use the values of A is equal to 2, B is equal to 6, and C is equal to 4. We are going to substitute those values in for A, B, and C in these various expressions, and then we're going to evaluate. We are going to find what that is equal to. We are going to simplify. So let's look at letter A. Letter A, we're going to start with, we're substituting in our values. So we have 3 times, letter A is 2. Now, when I substitute values into an expression or an equation, I always put the value that I substituted in parentheses. And the reason why is it helps to really show what it is exactly that you are taking out and putting in. Because when we substitute, we are taking equivalent things and swapping them. So if I took a $1 bill from you and I gave you 4 quarters, we have substituted. I gave you an equal value for what I had. So this is why, this is how it works in math, and we need to make sure we are knowing exactly what's being substituted, because when we start talking about negative signs, that is going to become important. All right, so we have letter A substituted in. We need to substitute letter B in. So I'm going to put that one in parentheses as well. We have 6, and we have 2 times our C value, which is 4. So now, my next step, I'm going to want to do these multiplication pieces. So 3 times 2 times 6. Well, 3 times 2 is 6. 6 times 6 is 36. And we are adding to that 2 times 4, which is 8. 36 plus 8 is going to give me 44. Notice I am showing my steps. Notice I am working my way straight down the page. That is what we expect you to do as you solve problems. Show your work, show your steps, and you are working down the page. And as you're working down the page, your problem should get narrower as you go, because you are simplifying and you are combining more and more things, so it should be getting narrower as you go down the page. All right, let's take a look at letter B. Letter B, we have a negative sign out in front. So we have -3, and we need to substitute in the values that we are using. So we are substituting in again, we're putting in 2 for A, and we're squaring it. And we have 4 times C, which is 4. Now, an important thing to note, exponents apply to the thing that they are attached to and only that. So what this says is we have -3 times 2 to the second power. Okay, so remember, order of operations, we are going to evaluate the exponent first. So -3 stays out in front. 2 to the second power is 4, and we have 4 times 4 still. So now we're going to do our multiplication step. -3 times 4 is -12. 4 times 4 is 16. And our final step is addition subtraction. So -12 plus 16 is 4. Letter C. So now we're substituting. Again, we see parentheses happening, but inside of the parentheses are B and C. So we have 6 times 4 in the parentheses squared minus A, which is 2, times B, which is 6. And I wrote B, 6, which kind of looks like a B. Okay, so we need to start by evaluating what is inside of our parentheses. 6 times 4 is going to give me 24. That value is being squared. We have minus 2. 2 times 6, we can do that multiplication right now. 2 times 6 is 12, and we still have that minus sign there. So 24 squared, you're going to probably need your calculator for that. We have 576 minus 12, and 576 minus 12 is 564. All right, so now you're going to try the U-try problems, D, E, and F, and you are using new values. So we're using A is equal to -2, B is equal to 6, and C is equal to 4. So A has changed up slightly. You'll notice we are working with the exact same expressions. And we're going to see how are we going to affect the problems by just making that first term, that A negative. So try the work and come back and check it against mine. So first off, letter D, we've got 3AB plus 2C. So we're going to substitute in what we know. So we have 3 times A, which is -2, times 6, plus 2 times 4. Okay, so now let's work through. 3 times -2 is -6, times 6 is -36, because we remember a negative times a positive is negative. 2 times 4 is 8. -36 plus 8 is going to give us -28. Okay? So, that's a little bit different than +44, all by changing that one A term. Same thing here, we're going to change the A term. So we're going to start off. We've got -3 parentheses. This is where parentheses are very, 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 very important, because we're still squaring the A term, and we have 4 times 6. Okay, why is this so important? When you type in your calculator is going to read things as strict order of operations. Meaning, if you type in, so let's just do a little calculator lesson off to the side here, that parentheses -2 squared does not equal -2 squared when you type it into your calculator. The reason why is, in this version, on the left, the entire thing, the negative sign and the 2, is being squared, because when we square it, we're saying -2 times -2, which would give us a +4. Okay, so you're going to get a +4 on that. Okay, now on the right-hand side, the negative is out in front. The exponent is only going to apply to the 2. So because what this is saying, what that negative sign says is we are wanting the opposite of 2 squared. That's the way your calculator reads negative 2 squared if you write it as I did on the right. So the answer you're going to get there, the opposite of 2 squared is going to be negative 4. And those are not equal to each other. So when you are typing in an equation or an expression and you are evaluating using a calculator, you absolutely must use parentheses. You must use parentheses. Because if you don't, you will get the wrong answer. And you're going to say, Mr. Bolin, my calculator gave me the wrong answer. And I'm going to tell you, no, it gave you the answer for the work that you provided it. It solved what you asked it to solve. You just didn't ask it to solve what you thought you were asking it to solve. All right, so enough of the digression. Let's go back to the work. Negative 2, the quantity negative 2 squared, I just said that was 4. So we have negative 3 times 4 plus 4 times 6. So now we can do this multiplication. Negative 3 times 4 is negative 12. 4 times 6 is still 16. No, sorry, this is 24. My apologies, 24. So negative 12 plus 24 is going to be a positive 12. Wait a minute, I copied this work wrong. My apologies. If we go back, we're going to do a little bit of an adjustment because here C was supposed to be 4, and I wrote that down wrong on my sheet. So C was supposed to be 4, so if we substitute that in properly of what I have written down, 4 times 4, we still have 4 there, and this is going to be 16. Negative 12 plus 16 is going to be a positive 4. So for this problem, we didn't change our value from the first time we did it with a positive 2 and the second time we did it with a negative 2 because that a term was being squared. It canceled out that negative sign. We're going to talk a little bit about that later on in the year. But there you go. We've got a 4 there with a slight digression and one slight mistake by me. Now, if we look at letter F, we are substituting in what we know, which is B is going to be a 6, C is a 4, and we are squaring that. And then we are subtracting. Our A value is negative 2, and our B value is still positive 6. So let's do the simplification inside the grouping symbols first. 6 times 4 is 24. And we are squaring that, and we're subtracting. We still have negative 2 times 6. So 24 squared, same as the last one, is still going to be 576. And we are going to subtract. We've got a negative 2 times positive 6, so that's negative 12. Now, you guys have learned this. You've gone over this. Subtraction is the same as adding the opposite. So instead of saying minus 12, it is adding positive 12 to this problem. And 576 plus 12 is 588. All right, we have one last problem in this lesson, and it is to write and evaluate an algebraic expression. In 2004, Chad Fell set the record for the largest bubblegum bubble blown. Assume that the bubble was spherical. The surface area of a sphere is 4 times pi multiplied by the radius squared. Write an expression that represents the surface area of the bubble. So if we do this in words, real quick, it's already written in words there, but it's 4 times pi, or if you want the symbol, times radius squared. All right, so now define a variable. What is the unknown value that we have in our setup? And it's going to be r. We don't know the radius of that bubble. Okay, so we don't know the radius. So now we substitute in our values that we have, and we know that it is 4 times pi times the radius squared. 4 pi r squared. So we want to know, the second part of this is the record-setting bubble had a radius of 25.4 centimeters. Find the surface area. So we have 4 times pi and that is times 25.4 squared. 25.4 squared. And now let's do the math on that. So we have 4 times pi times 25.4 squared gives us 645.16. And now you can multiply that out. You can abbreviate pi to just 3.14. So that's going to be what I'm going to use in these calculations. So 3.14. So 4 times 3.14 times 645.16, and you're going to get 8,103.21 centimeters cubed, or squared, centimeters squared. Now, I just rounded this off to 2 decimal places, even though it goes to 4. If you used the pi button on your calculator, you use the full irrational number, then you're going to get a slightly different answer than mine, but it won't be different by much. It'll just be different by a couple tenths. Okay. All right, those are our notes for lesson 1.2. If you have any questions, please bring them to class tomorrow, and we can address them then. Have a great day.